Okay, so this lesson we're going to be constructing chemical formulae. It's still on the syllabus outcome, investigate the nomenclature of inorganic substances using IUPAC naming conventions. So technically this one isn't part of the syllabus at this point, but it's a very important skill for everything else that we need in chemistry. So quite often you'll be given a word equation and you'll need to convert it to the chemical equation. So this is the important skill that we need for that. Okay, so firstly, there's a bit of revision just at the top of page 69. So have a go at that. Once you're done, we'll move on to the answers. So let's have a look. Ionic compounds are usually made of a metal and a non-metal. The metal comes first, the non-metal is then converted to the iode form. With covalent compounds, they're usually both non-metals. Again, this isn't a hard and fast rule, but it's most of them are like that. Most electropositive atom comes first, then the other one becomes an iode. So remember the least electronegative comes first, also called the most electropositive. And electronegativity increases as we go up and to the right on the periodic table. Now we use prefixes to show how many there are of each. Again, ignoring that first mono. So last lesson we took chemical formulae and we named them. This lesson we'll be doing the opposite. So we're going to take the name of a compound and construct the chemical formula. Okay, so this is arguably the more important skill because quite often we're given the words, we need to construct the chemical equation. So due to the way covalent compounds are named, it's easy to determine the chemical formula for them. So step one, we identify the atoms in the molecule. We then use the prefixes to determine how many of each atom there are. Remembering if there's no prefix at the start, then a mono is implied. So doing an example, determine the chemical formula of nitrogen dioxide. So what we do, we examine the names, examining the name shows that it's a compound of nitrogen and oxygen. There's no prefix out the front, so it implies it's a mononitrogen compound. Di in front of the oxide shows that there are two atoms of oxygen. Okay, so putting that all together, the formula is NO2. Okay, nice and easy. Our next example is determine the chemical formula of sulfur trioxide. Again, we have a look at the formula. It's a compound of sulfur and oxygen. There's no prefix at the front of the first one, so it implies that it's a monosulfur compound, so there's one sulfur. We have a tri in front of the oxide, which means that there are three atoms of oxygen. So putting it together gives us SO3. So nice and easy. So have a go at these ones. So we have sulfur dioxide, dinitrogen monoxide, dihydrogen monosulfide, sulfur hexafluoride, dinitrogen tetroxide, and phosphorus pentachloride. So have a go at those, pause the video, and when you're done, check through with these answers. Okay, first one, sulfur dioxide, SO2. So there's no mono out the front, but it's implied, and there's a di in front of the oxide, meaning 2. So we get SO2. Now, dinitrogen monoxide. Di in front of the nitrogen tells us there's two nitrogens, one oxygen, so N2O. Dihydrogen monosulfide, so the same again, there's two hydrogens, one sulfur, like so. Sulfur hexafluoride, so this is one of the rare times that we're going to get one up above tetra, but you should all know hexa by now, hexagon, 6 sides, so hexa is 6. So there's no mono at the front, but it's implied, so there's one sulfur, 6 fluorines. Dinitrogen tetroxide, we did this as an example going the other way in the last lesson, but dinitrogen, so 2 nitrogens, tetroxide, 4 oxygens. And lastly, phosphorus pentachloride. There's nothing out the front of the phosphorus, so it's implied a mono, so it's got 1. And pentachloride Yeah, so penta is 5, so 5 chlorines, PCl5. Okay, so ionic compounds. So ionic compounds are a bit more difficult, but once you get the process down, it's actually quite easy. So to determine the chemical formula for ionic compounds, um, it doesn't contain any indication of how many atoms there are of each, so we need to figure it out. Okay. The key thing to this is that ionic compounds will always have an overall neutral charge. Okay. Ionic compounds don't like to exist as a charged thing. Okay. Uh, Whenever we have an electrical charge, it wants to attract the opposite electrical charge, and with matter, it's going to do it quite strongly. So that's why things like to be neutral. So basically, what this means is that the number of positive charges and the number of negative charges need to balance out. So what we need to do is you need to know how to determine the charge on S and P block elements for this. So we've done this in the lesson where we looked at some of the octet rule stuff. So this was shown to you a while ago. So having a look at this condensed periodic table where we've got group 1 to 13, 14, 15, 16, 17, 18. Okay, so we'll just label them 1 through to 8 for now. That used to be the old naming convention. Um, and it's also how many electrons are in the valence shell. So remember, groups 1, 2, and 3, they like to lose electrons. Group 1 will lose 1, 2 will lose 2, 3 will lose 3. Our group 4 stuff, so our carbon, silicon, germanium, that could go either way. So it could go +4, -4. 5 refers to accept electrons, so it likes to become negative. So 5 is going to gain 3 electrons, 6 is going to gain 2, 7 is going to gain 1, and our noble gases, because they've got full outer shells, they're not going to do anything. So basically what that comes to is these charges. Okay, so remember these when we're doing the compounds with the S and the P block stuff. Okay, so it's what we're going to have to look at when we actually come to figuring out the charge. So let's have a look. Our first example, a nice easy one, determine the chemical formula for sodium chloride. Now everyone's going to shout out at me, NaCl. Okay, but how do you get there? Well, at the moment, you guys I'm sure you've just memorized it. But how do we get to it? Why is it just NaCl? Why is it not Na2Cl? Why is it not NaCl2? Why is it not NaCl5? Okay, this is how we do it. First atom we look at is sodium. So that's the first one. Go back to that table. Hold on, let me find out where the actual table is because I'm pretty sure it's in your booklet somewhere. Sorry about this. No, I didn't actually put it in your booklet. That's okay. But just have a look at your. Actually, there's a good one on page 32 that has a whole bunch of charges on it. Okay, so you can use that as reference if you want, but just remember those patterns. The first column is a +1 charge, second column is +2, so on and so forth. Okay, so go and have a look at that table. So sodium actually gives us a charge of +1, so it's lost an electron. We'll look at the second atom, which is chlorine. So chlorine as an ion exists as a -1 charge. So again, if you're not sure, check that table that I was just talking about. It was page 35. Now, +1 and -1, they balance each other out. So one sodium balances one chlorine because a +1 balances a -1. So that gives us an overall neutral charge on sodium chloride, so it's just NaCl. Now, a little bit more complex. Determine the chemical formula for magnesium chloride. So, having a look at the first one, magnesium. Magnesium's in the second column, so it's actually going to be a +2 charge. Chlorine is the second atom. It's in the second last column, so it's going to be -1, same as the last question. Now, unfortunately, plus 2 and minus 1 don't balance out. So plus 2 minus 1 still gives us plus 1. So it's not balanced. We need to balance that charge. Now, the way we do that, we do what we call a cross multiply. Now, it might seem super easy for something like this, but once we get to some that are a bit more complex, just following this method works a treat. Okay, so what we do is we take the coefficient of the charge and multiply the other atom by that number. So here we've got Mg2 plus Cl minus. So the coefficient of the charge of magnesium is 2. So we're going to make sure there's 2 chlorines. Coefficient of charge of chlorine, it's not shown, but remember that's implied that it's 1. So it's a 1 minus. So we take that 1 and put it down the bottom. Okay. And so that gives us MgCl2. So again, remember the 1 on the magnesium is implied. So that's our formula for magnesium chloride, MgCl2. And we can keep following this method through for all the other ionic compounds. Okay, so I've messed up that animation. So it's giving you the answer, but let's actually figure it out. So determine the chemical formula for aluminium bromide. So we have Al3 plus. Okay, so remember aluminium's there in the 3 plus column. Bromine's in the second last column, so it's a minus. We take the coefficients of the charges, cross multiply, so we get the 3 down next to the bromine and a 1 down next to the aluminium, which again, they're all implied, so we leave them out, which gives us that AlBr3. Okay. Now, determine the chemical formula for the following covalent compounds. So I'll get you to pause the video, have a go at these 6 questions, and then we'll go through the answers in a sec. Okay, so let's have a look. Potassium fluoride. So potassium exists as K plus, fluorine exists as F minus. Okay, so again, if you're not sure where those come from, go check that table on page 35. We can see that there's a 1 and a 1, so they balance out. That gives us Kf. Next, magnesium oxide. So there's Mg2 plus O2 minus. So here we don't actually have to cross multiply because they already balance out. So 2 plus balances with a 2 minus, so we just get MgO. Next we've got sodium oxide. So sodium exists as Na plus, oxygen is O2 minus, so they're different. So once they're different, this is where we need to do the cross multiplying. So we take the 2, put it down next to the sodium, we take the implied 1 and imply it down near the oxygen. So it should give us Na2O. So that should be O. This one's full of mistakes, so I'll go back and fix them up. Beryllium chloride. So if we have a look, beryllium is in the second column, so it's going to exist as a 2 plus. Chlorine is in the second last, so it's going to exist as a minus. So again, we have to do this. Take the 2 down, put it here. Take the 1 and imply it down here. Okay, so we should get BeCl2. Now, cesium nitride. So cesium's in the second column, so it's Cs2 plus. Nitride's in the fourth last column, so it's group 14, I believe. But either way, it's a 3 minus. Okay. Now we take the 3 from the nitrogen, pop it down next to the cesium. 2 from the cesium down next to the nitrogen. So we should hopefully get CS3N2. And lastly, aluminium oxide. So aluminium is a 3 plus molecule. Oxygen's a 2 minus. So we take the 3, pop it down next to the oxygen, and the 2 down next to the aluminium, gives us Al2O3. So hopefully you got those right. If you're still not sure, come and see me. but we're going to do a few more examples now. So we're going to move on to some further rules. So some advanced rules. So names of transition metals. They will always have the charge of the metal in Roman numerals in brackets after the name of the metal. So for example, iron 3 chloride gives us an iron 3 plus ion. Okay. Iron 2 chloride would have an iron 2 plus ion. Okay. Now this is important because a lot of transition metals exist as multiple different um, ions. So if you go back and have a look at that table on page 35, is it 35? No, it's not 35, sorry. 32. I've been saying it wrong. Page 32. Most of the transition metals have multiple charges listed there. Now, some of them don't, but they do still have multiple charges. Okay, they're just not very common. Now, of all of those, we don't really deal with too many of them, but we do give you the charge in that Roman numerals. Okay, we do. There are two exceptions that you will need to remember though. Okay, and they are zinc, which has a 2 plus charge, and silver, which has a +1 charge. Okay. So they're the only metals that you'll need to remember that are outside of that S&P block. So of the transition metals, remember those two. Um, any others, you may be able to get some information off the formula sheet if you need it, but you should get given most of that information. The other thing you need to memorize is the charge on some polyatomic ions. Okay, so again, this table, I've just copied and pasted it from last lesson. But basically, you need to remember those charges. So you need to remember that carbonate is 2 minus, nitrate is 1, nitrite is 1, sulfate and sulfide are 2 minus, phosphate's 3 minus, and hydroxide is 1 minus. Okay? Again, because when it comes to doing the formula, we need those charges. So you won't be given this in the exam, so you'll have to remember the charges on this. So let's put it to I messed up the animation again. Let's do some examples. So iron 3 oxide. So iron 3 gives us an Fe3 plus charge. Oxygen's a 2 minus charge. So again, we take that 3 down to the bottom of oxygen, take the 2 down to the bottom of iron, and gives us Fe2O3. Determine the chemical formula for zinc phosphate. So zinc, remember that's one that you have to memorize. It exists as a 2 plus. Phosphate, another one you have to memorize, exists as a 3 minus. So we take the 2, pop it next to the phosphate, the 3, pop it next to the zinc. And remember, when we're dealing with polyatomic ions, we need to put them in brackets and put how many of them there are outside the brackets. So in this case, we're going to put the 2 outside the brackets, and the 3 for the zinc just pops on the zinc. So it gives Zn3, PO4 in brackets 2. Now, there's just one more rule. We're not going to do an example of this, but ionic compounds are always quoted as the simplest ratio possible. Okay, so for example, if we did titanium oxide, okay, we'd notice that the titanium's got a 4 plus charge, oxygen's got a 2 minus, so we'd cross multiply and we'd get Ti2O4. But that technically doesn't exist like that. Okay, so it exists as TiO2. So because both of them are divisible by 2, we just find the simplest ratio and change it to that. Okay, so with those rules, have a go at these 6 questions. Okay, so remember the Roman numerals in the brackets, the charge on that first atom. Okay, and then do our cross multiplication. So iron 3 iodide, that gives us Fe3 plus, I minus, cross multiply, we should get FeI3. Vanadium V oxide, so V is 5, so it should give us V2O5. Chromium 6 oxide should give us Cr2O6, but they're both divisible by 2, aren't they? So it should just be CrO3. Magnesium hydroxide, so magnesium's 2 plus, hydroxide's 1 minus, so hydroxide's going to end up with 2 of them, magnesium is going to be 1, and the OH will be in brackets with a 2, so MgOH2. Copper 2 sulfate, so copper is a 2 plus, sorry, copper 2 is 2 plus charge, sulfate is 2 minus, so they're going to balance each other out, and it's just going to be CuSO4. Now titanium 4 phosphate, so there's a 4 up charge on titanium, a 3 minus charge on phosphate, so we bring the 3 down to the titanium, the 4 down to the phosphate, and we get that. Okay, if you're still not sure what's going on, come see me and I'll try and run through it as best I can with you. Now, bit of a summary for today's stuff. Chemical formula of covalent compounds follows the mono, di, tri prefixes. So it's just, if it's mono, there's 1, if there's di, it's 2, tri, etc. So it's nice and easy to actually produce the chemical formula for covalent compounds. And remember, for covalent compounds, it's usually 2 nonmetals, as we said in the revision today. Now, for ionic compounds, you need to know the charges. So you need to refer back to those tables. Page 32 is an excellent help for that. Then we cross-multiply the charges to figure out the correct ratios, and always use the simplest ratio available. So once you've written down that summary, go into the questions on page 74.